When we think of a computer today, we imagine something silent and microscopic, tucked away behind a glass screen or inside a sleek aluminum shell. But in the mid-20th century, a computer was a physical, mechanical environment. It was something you walked inside of. It hummed with high-voltage electricity, radiated an intense heat, and filled the room with a rhythmic, percussive clicking sound. To understand how we went from mechanical levers to the digital age, we have to look at the two components that made it possible: the electromagnetic relay and the vacuum tube. The earliest form of a digital switch wasn't electronic at all. It was electromechanical. This is the relay. At its heart, a relay is just a remote-controlled light switch. It consists of a coil of wire wrapped around an iron core and a movable metal arm called an armature. When electricity flows through the coil, it creates a magnetic field that pulls the arm down, making a physical connection. When the power stops, a spring pulls the arm back. This simple mechanical movement allowed one circuit to control another, separated by nothing but magnetism. By wiring these relays together in specific patterns, engineers could perform logic. If you connect two relays in a series, electricity only flows if both are closed. This is an AND gate. If you connect them side by side, electricity flows if either one is closed and or gate. In the 1940s, machines like the Harvard Mark I used thousands of these clicking metal arms to solve complex differential equations. It was a computer you could hear thinking, a massive chorus of metal striking metal, processing data at the speed of mechanical motion. However, relays had a fundamental ceiling. Because they relied on physical parts moving through space, they were slow. A relay can only flip back and forth a few times per second before the metal begins to fatigue. They were also prone to environmental interference. Dust, corrosion, or even a small insect could wedge itself between the metal contacts, preventing a connection and causing a calculation error. This is where we get the term computer bug, famously coined when a moth was found trapped inside a relay in 1947. To move faster, we needed to remove the moving parts entirely. We needed a switch with no mass. The solution came from a discovery made by Thomas Edison and later refined by John Ambrose Fleming: the vacuum tube. Inside a sealed glass bulb, a filament is heated until it glows orange. This heat gives the electrons in the metal enough energy to break free and create a cloud of negative charge around the filament. In a vacuum, these electrons can fly through empty space without hitting air molecules. In a basic tube, called a diode, electrons flow from the hot filament to a positively charged plate at the other end. But the real breakthrough was the triode, which added a third element, a metal grid placed between the filament and the plate. By applying a small voltage to this grid, you could repel the electrons or let them pass through. The grid acts like a tap on a sink. A tiny amount of energy at the grid controls a much larger flow of electricity through the tube. The switch was now purely electronic. Because electrons are nearly weightless, they can be switched on and off millions of times faster than a mechanical relay arm. This jump in speed changed everything. It meant that calculations that previously took hours could now be completed in seconds. But this speed came at a cost. Vacuum tubes are essentially specialized light bulbs, and like light bulbs, they are inefficient. They generate a tremendous amount of waste heat, and eventually, the filament simply burned out. Maintaining an early computer was a constant battle against hardware failure. The ENIAC, completed in 1945, was the pinnacle of this era. It contained nearly 18,000 vacuum tubes. It occupied a room the size of a small house and consumed 150 kilowatts of electricity, enough to power a small neighborhood. When it was turned on, the heat was so intense that the room required massive industrial cooling fans just to keep the components from melting. Despite the heat and the frequent tube failures, ENIAC proved that electronic logic could handle the most complex problems humanity had ever faced. By using heat and glass to manipulate the path of electrons, we learned to translate human thought into a binary language. We built machines that could memorize numbers and make decisions based on logic gates. The vacuum tube was the bridge between the world of steam engines and the world of software. It taught us how to control the smallest particles in the universe to do our work. Every time you open an app today, you are using a descendant of those glowing glass bulbs and clicking metal switches. Eventually, the vacuum tube would be replaced by the transistor, which did the same job using solid crystals instead of heated filaments. The transistor was smaller, cooler, and more reliable, but the fundamental logic remains the same. Whether it is a mechanical arm snapping shut, a cloud of electrons passing through a grid, or a pulse of electricity through a piece of silicon, the goal is the same: to create a switch. These switches are the building blocks of our modern reality, proving that with enough light and heat, we can make matter think.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.